Oh, we can't see anything.
Yes, registered. Okay. Someone in the chat, someone saying something. Okay. So shall I start? Oh, wait for some time.
Sure, go ahead. Yeah.
Okay, sure. Hello all. So today is the topic about diffusion. So basically, I just want to give a overview, understanding or imagination about diffusion, how the diffusion is happening, all this process. So this is the outline of today's talk or lecture. So first thing is like sampling and diffusion. I'll start from the Bayesian perspective. From the Bayesian perspective, then I will introduce Langevin dynamics. So the reason for introducing these two topics is that to highlight that everything is related. I mean, diffusion, whatever we are doing in the diffusion is not something new. It's something already existing thing. We are just adding something for the sake of diffusion or generative thing. So that is the reason why I'm introducing those two things. Then followed by diffusion, and followed by, at the end, I will introduce discrete diffusion, what are the challenges and some existing paper. So I'll start with the Bayesian thing. So in the previous lectures, we already introduced about the Bayesian thing. Like, so for example, so I will start about the neural network. So if you have a neural network, we have certain weights and we want to learn over the weights. So for example, so this is the posterior given data. Posterior, it is given by likelihood, and this is the prior, and this is the marginal. Marginal is nothing but integral over entire theta. So let's say this is a constant because we are integrating over the theta. It is constant with respect to theta, right? So what are the challenges computing this posterior in the closure? So why we need this actually posterior? So when we are doing some inference, that is a testing a sample, we also need the uncertainty in its prediction. Like we know that in general neural network, it's makes a prediction. Okay, this is dog, this is cat, but what is its confidence? I mean, confidence is an separate parameter, but we assume that the softmax. Okay, when we are labeling, we have two classes. We compute the softmax. Softmax is what is the? It's like a probability, right? 90% it belongs to dog, 10% it belongs to class. But that is not the confidence actually. That is relatively. Yeah.
No, just not my show face.
Yeah.
Yeah.
That
Go
is
ahead.
relative. But we are saying that, okay, 90% below, it's a dog, 10% it's a cat. But how much confident that is the 90% is the dog? That is a separate parameter. Okay, in traditional neural network, we don't have that. But in Bayesian thing, we can compute that. How? Let's say we have a, uh, uh, let's say it's for the classification, multi-class classification or binary classification. We start with the prior. Generally, it's a Gaussian distribution or any other distribution. And likelihood is generally cross entropy. We also derive the cross entropy, all those things. So this is the posterior. So generally, as I said, this is the prior. Prior is like minus infinity to infinity. Okay, this is prior. But likelihood, if it is a nonlinear neural network of multiple layers, it has multiple local minima. Okay, and in terms of so the likelihood will be it's something like this. And when we multiply prior and posterior, uh, it's weighted combination of something. So this, you can think the inverted is a multiple local minima, but here we are looking from the perspective of the probabilities. So higher the probability means there is the loss is very less. Okay. And okay, now during inference, how we test a sample. Okay. Next we have X star. X star is our testing sample. Okay, these are Y and X are the training data set, and we have an X star, and we want to compute what its class label or anything. So how we compute P of Y star, what its class label, given X star, comma, theta, is nothing but integral of P of Y X star. Sorry, it's not theta. It's given X comma Y, theta, and this is posterior. So here what we are doing, we know this is a training data set. We know that this is a training data set. I have given us some test sample. What it is probability of belonging to a particular class. So what we do is that we integrate over the all the possible weights. In neural network, we only look at the single weight, right? That is point estimate. But in Bayesian thing, we look at all the possible weights. Okay. So, for example, if there are 10 weights, generally it is infinite, but if let's assume there are 10 weights, out of 10 weights, 6 are saying as dog and 4 are saying as cat, then the confidence is 60%. So not everyone is confident about its prediction. So that is how we compute the confidence. So it's like asking multiple peoples, if everyone agree on the prediction, we say that it is 100% dog. But if you 50% says dog and 50% says cats, then it's not confident. And what its application is, the critical applications like medical. Like if we have a Bayesian neural network model, it's predicting a cancer, but it's only 50% confident. Then we go to a doctor. So in this way, we are reducing the burden on the doctor. So that is the importance. But here, this posterior, the posterior is not in a closed form, because our likelihood, even though prior is our Gaussian, our likelihood, because of this nonlinear activations and multiple layers, we cannot compute this Z normalizing factor. Okay. So at least what okay, we are not able to compute this integral. Can we do something like Monte Carlo? Monte Carlo, something like y star given x star given theta. So where this theta I, let's say this is I, this theta I, and how theta i's are coming from p of theta given x comma y. So some way we need to sample from the posterior. Again, the challenge here is that we cannot sample from the posterior, but can we sample from the posterior to get end samples, and we take the average prediction over the ends. This is Monte Carlo. As n tends to infinity, we are actually approximating the actual posterior. Okay. Here it's okay. Sorry. Okay. Until here it's clear, right? Any doubts?
Yeah, so the biggest problem is actually the denominator.
Yeah,
We
yeah.
cannot calculate it. So if anyone or someone someone joined. Okay. Yeah, I think that's a lot of people doing those Monte Carlo sampling or bidirectional inference
Yeah.
because of the denominator.
Denominator, yeah. So, okay. So the thing is that how do we sample? And we need to sample for, okay. So let's say this is the posterior. Okay. And there are different techniques like Monte Carlo Markov chain with metropolis hasting, or importance sampling, or rejection sampling. There are different ways of sampling from the posterior. But here today we will discuss about the gradient-based sampling, which is again related to diffusion. And this gradient-based sampling, it's already existed in the literature. Like the main title of this paper is that Bayesian learning via stochastic gradient Langevin dynamics. So, okay. So gradient based sampling this is. Okay. So again, this is our posterior. So we cannot compute this in a closed form. So the goal is that, okay, what should happen? If I start from a random point, because we don't know what is the exact posterior. So we start from a random position. Let's say I started from here, okay, theta 0. And I need to push this theta 0 such that it covers this region. Because these are the samples. Because these are the neural network weights which makes correct prediction. So we need to push this theta 0 towards the posterior. Like we need some measurement. Like this is theta 1, this is theta 1, this is theta 2. And after some theta n, this is called burn-in period. Burn-in period in the sense, it's also, this terminology also available in MCMC. These are not the correct samples. These are only the initial samples. After some 1,000 iterations, we will move to the actual posterior. So after reaching this posterior, we need to collect again. If we only stick at this point, what it becomes, we are taking only one point, and it's like kind of overfitting. But what Bayesian requires some different kind of samples also. So we also need to get theta n plus 1, theta n plus 2. So we need to cover all these samples. I mean, what I'm trying to say is if we once reach the mode, you should not stick at the mode, but you should also oscillate across the posterior, but it should not also escape the posterior. That is the goal. Okay. Okay. Let's see. Now, intuitively, so let's say this is theta t and this is theta t minus 1. So I said gradient based thing, we can compute gradient of theta, p of theta given x comma y. What is this posterior? If we compute the gradient of the posterior at this point, we are making a gradient ascent, right? So we are moving towards the posterior. Now, what is this posterior? Posterior is nothing but our likelihood, right? Likelihood, theta, and multiplication, right? P of theta by z. Okay. But here, if you look at this thing, the z is still there. Okay. How to get rid of this thing? I mean, how to get rid of z without compromising the computation correctness. So one simple thing what they do is that apply log. Okay. If you apply log over this thing, what will happen? Theta t equal to theta t minus 1. I mean, now earlier we are doing in the exponential domain. I mean, log of exponential of log is the true one. But now we are doing in the log domain. So what's happening? Delta theta log of, if I apply log over this posterior, what it becomes? This multiplication becomes addition. And this numerator goes into the subtraction, right? Y x comma theta plus delta t log p of t. This is delta log z. Any ideas what will be the value of this part? 0. Any others? Why it's 0?
Because z is supposed to, when you integrate it,
Because we gradient regarding to the thing.
Yeah, regarding with the
Yeah,
theta. And what is z? We are after it's obtaining after integrating all the theta. So it is constant with respect to
Yeah,
theta. It's constant. So doing this simple arithmetic operation, we got rid of theta. Okay. Now we can do it looks like a general stochastic gradient descent, right? Stochastic gradient descent, and we can add epsilon like a learning rate epsilon, and generally they suggest that epsilon t like start with the higher learning rate, gradually reduce it, epsilon t tends to 0. So they also have some condition epsilon t, so maybe we can discuss that later, but this is kind of learning rate. Okay. Now, so this thing, if anyone has an idea, so here we are maximizing the posterior, right? So anyone has an idea how this is connected to neural network? Like this expression is somewhat connected to training the neural network. What is that?
gradient descent.
Yeah,
Gradient descent.
I mean, it's like a network is like a likelihood maximization, right?
Yeah, likelihood maximization
With a regularization.
with a regularizer. Okay. So how we can, so if you look at this thing, now we'll look at this expression. Okay. Log of p of y x comma theta. So here we are doing classification, that is multi-class classification. Only one of the class label is it. So the question is, what is the likelihood of, so it's multi-Nolly classification, right? Right. So what is the likelihood of multi-Nolly classification expression? You understand my question? Likelihood of multi-Nolly probability, or expression. What is that expression?
It's you have to multiply initially, right?
Yeah. What is that expression? It starts with Bernoulli. Let's start with Bernoulli, right? What is the probability? Let's say P is the probability of success and Q is the probability of failure. So what is the likelihood? Or how to write this as a mathematical expression?
P to the power t.
Yes. Yes. So for Bernoulli, Bernoulli, what is the likelihood? P of X.
Okay, yeah. Oh, okay. So,
Yeah. So X can take only 1 or 0, right? In Bernoulli, X can take only either 0 or 1. So we can write P power X into 1 minus P power 1 minus X, right? When X equal to 0, it's P. When X equal to 0, it's 1 minus P, right? So similarly, can you say about what is for multi-Pauli? Not nominal, multi-Pauli. Multi-Pauli in the sense, it's like a dice.
Yeah.
Yeah.
Okay. So it should be pi to the power xi
True.
and all multiplied.
Yes,
Yeah.
nice, nice. So here, so there are now we have a dice. Imagine a dice. Every face has different probability. Let's indicate it with pi, pi 1, pi 2, pi 3, pi 4. Okay. And when you roll a die, only one side is shown. So it's not like two sides are shown, right? At the time, only one is correct. So for that, multi-known is nothing but pi 1 power x, let's say, pi 2 power x. I mean, x is, oh, sorry. Let's say pi 1 power y1, pi 2 power y2. If there are n classes, yn. And this y1, y2, yn is a one hot encoder. Only one is true. So this is the multi-Pauli likelihood. Now for we are doing multi-class classification, right? So apply this likelihood. Log of p of y x comma t is nothing but we are applying log, right? Y1 will come here, right? Y1 log pi 1 plus y2 log pi 2 in this way. So this expression looks like anything in our neural network. This pi 1 or pi 2 are normalized like 0 to 1, like applying after softmax. Cross entropy, that's it. Cross entropy. So this is cross entropy. Okay, nice. Next, look at this thing. How this is a regularizer. So we said that this p theta is a normal distribution, right? What is the normal distribution looks like? 1 by 2 root 2 pi sigma square e power minus theta z. It's a mean, let's say 2 sigma square, right? And what we are doing, we are taking the derivative with respect to theta on log. Okay. So log this multiplication becomes addition and this is constant, it becomes 0, right? And this is exponential. Log of exponential is down. So now delta of theta log of 2 sigma square, and if sigma square is 1, so this is looks like L2 regression. So what we are doing, this is we are maximizing the posterior. Maximizing the posterior is nothing but cross entropy loss with L2 regularization. So here we saw the connection, okay, Bayesian and how is connected to the neural network. Okay, but the problem with this thing is that, okay, we are gradient ascent, right? This is a gradient ascent. Okay, again. So we have started from here. It moved, it's a gradient ascent. It moved, and this is the maximum point. And it won't, but we need samples from everywhere, right? It's not only from here. So what is the thing is that add some noise. For this expression, let's say I will.
Sorry, so why
Okay.
Can you explain this again?
Yeah. So if we use this expression,
Yeah.
if we use it, this is gradient ascent.
Yeah.
So gradient ascent, if we start from here, it moved to this point, and this is the maximum.
Yeah.
It's always moves to the gradient ascent, right?
Yeah.
So it's stuck at this thing. Even how many iterations we do, it will stuck over there.
Okay.
But for Bayesian perspective, we need neighborhood samples too.
Oh,
From
I see.
here.
Oh, I see your point.
Yeah.
Yeah, that has been a big problem in MCMC for a long while.
Yeah, in MCMC, the other problem is that covering the multiple mode.
Yeah, if you have multiple nodes.
Here, even though it is one mode, we are not able to cover the entire posterior.
I think yeah, I mean the multiple mode problem is the reason why people invented Diffusion.
Yeah.
This is a different problem. It's like
Yeah.
you only have half of your peak.
Yeah.
Get it.
Someone. Yeah, please. Someone has any question?
No.
Okay. It's okay.
Sorry.
Okay, please continue. Online people, someone saying something.
I just wanted to, how did you go from multi-nollie to entropy? I missed that link.
Okay, okay, no worries, no worries. So you understood the multi-nonny expression, right? Sorry for my bad
Yeah.
hand. So this is this thing, right? Okay. And if you apply log of this thing,
Exactly.
the log, so this do you again understood? This is the next step,
Yes, you took the log of the whole expression.
log of the whole expression. So this is y1 log of pi1 plus y2 into log of pi2, right?
Yes.
So this pi1 and pi2s are probabilities, like
Mm-hmm.
pi1 plus pi2 and so on, pi n is equal to 1,
Mm-hmm.
right? So if you look at, so these are all functions of theta. We are dealing with a neural network,
Yes.
right?
Uh,
So in neural network, what is the end of the layer? If there are 10 classes, we apply softmax, right?
mm-hmm, mm-hmm,
So this pi1 is nothing but pi1 is equal to e power w1 transpose x and sum of all,
mm-hmm. Right.
sum, right?
Mm-hmm.
So this is softmax, right? And
Mm-hmm.
what is cross entropy? Can you say cross entropy expression?
No, I cannot. But I'll. Yeah. It's the
Okay, no worries.
probability of like. Okay, please go ahead.
Okay. You know the entropy expression, right? Okay, entropy expression, generally what is entropy expression? Pi p negative of pi log of pi. This is entropy,
Right,
right?
and cross entropy would be two different
Between two
distributions, like
different distributions.
probability. Yeah.
Good. Next, here, y yi log of pi I, right? This
Right.
is cross entropy. This is cross entropy, right?
Mm-hmm.
So, so here generally we want to minimize the cross entropy because cross entropy is negative. I mean, PyTorch or anything. But here we are want to maximize, and there is a positive sign.
But for cross entropy, please correct me. It's that we have a target distribution and we have a like the current distribution, right?
Yes, yes, yes,
Cross entropy.
yes, yes,
And when we minimize the cross entropy, we aim to say that how similar is our current distribution to the target distribution,
yes,
right?
yes. And what
So
are the distributions here?
how
This
are
is
we interpreting yi log pi I as cross entropy?
okay. Okay. What are the distributions we are dealing? Generally, it's multi-nollie distributions, right?
Right.
So multi-nollie distributions, this yi, y2 are one-hot autoencoders. Sorry,
Okay.
one-hot vectors,
Okay, right.
right? So that is also a distribution, right?
Mm-hmm.
And pi
But
one, okay.
sorry, no, so what I'm trying to understand is in a normal cross entropy, when I have a cross entropy expression, and when I minimize it, I say that I have a target distribution and I have a current distribution that
Okay.
that my
What is the target distribution?
mm, as in the, how do you say,
Neural
the
network.
true that's in the true world, right?
True world in the sense, I mean, for classification, it's one-hot encoder, one-hot vector, right?
Right, right.
So here also it's y1, y2 are one-hot vectors, right? I mean, only one is zero. Only, sorry,
Mhm.
only one yi is one. Rest of them are zero,
True. Yeah.
right? So see, this is one-hot vector, y's are, and
Mhm.
uh, these are the vectors learned from our neural network after softmax.
Right. Okay. Okay, I get it now.
Yeah, yeah. I mean, yeah, just cross-check the cross entropy loss in PyTorch and it's easy actually.
Yeah, yeah, sure. Thank you.
Yeah, no worries, no worries. Yeah.
The difference between traditional neural networks and this is that in traditional neural networks, we want to reach up, we want to converge to a point.
Yes, yes,
And
yeah.
here we want to do the ascent such that the final output acts like a sample from that distribution.
Yeah, yeah, yes, that's it. A different interpretation.
Yeah.
Different interpretation.
That's why the noise is required.
Noise, why noise is required is that if you remove the noise, it will also converge to this point.
Yeah.
And this is why noise is required to sample from the neighboring points. Okay. So generally, okay, this is our expression, right? I will put this in the L, okay, short form. So theta t equal to theta t minus 1 plus L plus some normal distribution. So what happens is that after our point reaches this point, okay, So next iteration, it will stay here because of this thing, because it's 0. But when we add this noise, it moves some point here.
Oh, so noise is adding to the gradient.
Yeah, gradient.
Okay.
Yeah, yes, yes. So what happening is, so this is all, these are burn-in period. We ignore it. So only the last 10 samples, we store it in a memory. Okay. So during this 10 samples, if you, at this 10 sample, you see, we are, because of this noise, it's moving away from here. Okay. At this point, the noise, this is greater than 0. It will again move back. But because of this noise, it oscillates. So it's kind of covering the entire posterior distribution. Okay. Now, after, even though if T is from 0 to 1,000, okay, only the last 100 or 10 samples, you will store it in a memory. And then you, while you making a prediction, you do Monte Carlo prediction. So any doubts?
So the purpose of adding the noise was just to increase the variety of samples.
Yes, yes, yes.
There's no other explanation for it.
That's it. Mainly that's it.
And you store 10 points in your memory, in your buffer.
Yeah,
and
yeah,
what
yeah.
do you use it for?
Prediction.
Prediction.
Yeah, during
Oh,
inference.
okay, the Q using a theta and making the prediction.
Yes, yes, yes. I mean, that integral is replaced with sigma.
Oh, okay.
Yeah.
Sigma. Okay, I get it. So
Yeah.
you do, so that will, you, after you run this for a long while,
Yeah.
the 10 samples will be somewhere around your peak.
Around the peak. Yeah,
And
it's
you-
kind of.
okay, so that will give you maximum likelihood. if you
Yes.
Do using this 10 sample which are around the peak. Get it?
Yeah.
Okay, I have a question. So remember it was 10 to 1,000. Is that time step or what?
Yeah. Like iterations. Like, for example, you want to do 1,000 iterations.
Oh, it's not the denoising step. It's
Oh, no, not the
it's not-
denoising step.
okay.
Number of steps.
Okay.
Yeah. So you.
Yeah, I got.
Yeah. The theta 0 is the noisy one. I mean, it's not the local min or anything, right? So we go to the local minima, and they, because of this noise, we able to sample the entire posterior. Yeah.
Are there any conditions we can impose on the noise so that the samples are much more resembling of the original distribution? So
Because we don't know what is the original distribution. So what is the, what indicates is the distribution is that this log of pi, log of P of Y. Because if the log likelihood is high, then the sample is from that posterior.
Yeah.
So that is only the indicator we have. Yeah. So yeah, it has problems. That is a different thing, but I just want to highlight it. For example, if there are multiple modes, okay, if something like this, okay, this is non-zero, right? The probability is non-zero. It might escape. I mean, it might cover, even though it starts from here, because of this noise, it might move here. Because there is a log likelihood, it's not 0. But when there is a multiple modes with non-zero, I mean, they're completely disconnected, then it's not easy. Not possible to cover the entire modes. Then different methods like G-Flownet. Sorry. Yeah. Sorry.
so you are seeing even in the diffusion case, although we add the Gaussian noise.
Yeah.
Face a problem.
Problem.
About
Because there's are distances, these are not connected.
Yeah.
So it's a problem. Okay. Yeah. So this what we have discussed. Okay, Bayesian, sampling, and Langevin dynamics. So this is the thing. Next. So as I said earlier, we cover 3 points until connection to traditional neural networks. Now we will come to the score function, diffusion thing. So diffusion. So again, diffusion, what is that? You have a set of, it's a generative model. It's a generative model. You have a set of data points, x1, x2, xn. And you need to learn the distribution so that you can generate new sample. Similar to that, but something different. So the problem statement is that x1, yes, nice. It's a brain. Right?
In case someone is sleepy.
Yes. So we will think from the same perspective, from what we have done there. Okay. So now we are doing the domain of X space, not the theta space. Okay. So let's say these are the input data points. Now I will say the iterations. Okay. So the thing is that this is the data distribution. We don't know where it is. We start from a random point. This is most probably, it's not a data point, right? If you randomly sample any point, it's not a data point. So you have to move towards the data distribution, okay? So let's say I will say them as x0 in terms of xt equal to xt minus 1, sorry, xt minus 1 plus something. What is this something? Because earlier for classification thing, we have something like cross entropy to move towards the distribution. But here we don't know anything, okay? So let's assume there is a true distribution of the data points, okay? Let's say we call it as P of X, okay? And this P of X is nothing but P, again, this is the numerator, likelihood, and Z is the denominator, okay? Let's say this is a true distribution. We don't know what it is. If we have the true distribution, I can write something like xt equal to xt minus 1 plus same thing, log of P of X. So if I start from here, let's say, so it is helping, right, to move towards the true data distribution, right? But the thing is that we don't know what it is. So let's use our neural network. But how to use that neural network? So here it's clear, right? The motivate.
The motivation is clear.
Yeah, good, nice. So now we want to learn a neural network, okay? So the simple expression is that, okay, expectation of x, P of X. Let's say we are using neural network. See, this is theta, not theta, sorry. This is x. Yeah, thank you. Log of P theta x. This is a neural network. Delta x log of P of X. So let's say if we have access to this thing, we could learn this thing, right? For every, you have some training data set, you will learn this neural network, its probabilities, and finally you will replace this thing with our neural network. But we don't know this thing, right? This is square, okay? I mean L2 norm, but we don't know this thing. So we need to some way get rid of this thing, but still able to learn our neural network, okay? So what is the goal of this expression? We want to minimize this loss with respect to theta, right? What is this goal? Minimization, argmin or anything, expression of same thing, right? We want to minimize this loss for a neural network of theta. Okay, it's clear.
Can you just explain this expectation term? Why do you have to subtract log p theta minus log px?
Oh, okay. We want to learn a neural network such that it minimizes this actual true distribution.
Okay.
Right? This is a true distribution. It's not there, but let's say it is there. So we want to mimic.
So this is the objective function. that you
Objective function.
previously defined.
Yeah, it's defined. Yeah.
Okay.
But here the problem is that we don't know delta x log of P of X. How to get rid of this thing? Okay, just expand this expression. Expand this thing. Expectation x given P of X. If we expand this thing, what will be delta x log of P theta x whole square, right? Plus delta x log of P of X whole square minus 2 into delta x log of P theta x, delta x log of P of X, right? So here, this is important. We are minimizing with respect to theta, right? So what is the thing which is not dependent on theta here?
The
Anyone?
second
Pesong will say.
Ah.
Sorry. Yeah.
Second term.
Yeah, second term.
Del X, right?
Yeah, all are del x.
Yeah.
Yeah.
Somewhere.
Oh,
del theta. What?
where? It's all x.
Yeah,
It's all
yeah,
x.
yeah,
Sorry.
Okay. Now
Yeah.
it's X.
Yeah.
Okay.
Yeah, sorry.
term. Okay.
Yeah, I looked like this. So, okay.
Now,
So the thing is that it is independent of theta. This part,
Second.
right? Okay, we got rid of one log P of X, but still we have one more thing, right? So if you look at only this expression, okay, if you look at only this expression, we are taking, and also remember that we are taking the expectation with respect to P of X. If you write this thing, if you forget this thing, this is nothing but delta x log of P theta x delta x log of P of X into P of X, right? Dx, because we are sampling from the P of X, right? Right? Any doubts?
The theta and the x are very similar.
Yeah, yeah. Yesterday I tried to write X in this way, practice, but now it's gone. Okay. So here these are X, okay. This is X, this is X, this is X. This is clear, right? We just replace this expectation with the integral, right? So now, if you look at this expression, what is this? Delta X log of P of X. We can write it, how we can write? Delta X log of P of X divided by P of X, right? Sorry. Yeah. Sorry. If you look at this thing, delta X log of P of X, how we can write? Log of X is the derivative of log X is 1 by X. But again, we are taking the respect to X, right? So delta X P of X divided by P of X. Okay. And this P of X got cancelled. But still we have this term. Okay. How to get rid of this thing too? Okay. Here comes the integrals. Integrals like what do you say? F of X, if G of X dx is there. Integral by parts. What is integral by parts? Anyone remember?
No.
Okay. This is nothing but F of X integral of G of X, yeah, dx, minus integral of F of X integral of G of X dx. Okay.
Now I remember.
Yeah. So if you shall we do an example or continue with this again? Okay. Okay. This is okay. And here one thing, okay. This is F of X, G of X, this is the thing. And if you look at this thing, we are looking at delta X log of P theta X and another term delta X PX dx, right? And you have to choose one is what should be F of X and G of X. If you choose, yeah, this one is F of X and this is G of X. It's nothing but, yeah, delta X log of P theta X. And we are taking integral with respect to this one. So what happens integral with this delta X P of X dx. So what is the value of this thing? We are taking the integral of a differentiation function. Same P of X. So this integral and this gets cancelled. And delta X log of P theta X P of X, right? And we have limits. This is a what is a finite definite integral, and definite integral because, and we are taking the normally we are minus infinity to infinity. Okay. And because this P of X, even though it's a true distribution, we are computing the P of X values of the end points. But end points, there is no data value or it's very small. So it becomes 0. Because we are substituting infinity in P of X, I mean extreme values into this expression, it becomes 0. Okay. And,
like how is P of infinity?
Yeah, it's like
small?
Oh, no, I mean, like it's we assume that our data distribution, it's something like a tail distribution,
Okay.
something. I mean, it could be multimodal, but it's a tail.
Okay.
Yeah.
Okay.
At the end, it's
There is
kind
no
of
support,
there is no support. Yeah.
Yeah.
So that is why it's 0. Okay. Again, we got rid of P of X. Now, what is the expression remain? This one, right? Next, minus integral of delta X log of P theta X integral of, again, integral of G of X in the sense it's P of X, right? P of X dx, right? So this is second expression. What is the first expression? This one, right? This is the first expression. Yeah. Expectation, label the expectation, integral of delta X log of P theta X whole square minus 2 into this one, right? Delta X log of P theta x. And for we are also integrating with respect to P of x. And here also we are respecting P of x dx. Is it clear? Okay. So this is the integral, right? We are taking integral with respect to P of x. But we don't have unlimited samples. We have finite samples. Replace it with Monte Carlo. Px is gone. So now this I equal to 1 to n delta x log of P theta x whole square. Okay. This is,
You have to divide by sample.
sorry. There is one more thing. Sorry for the confusion. So there is, okay, in that integral, there is one more delta x will come here. This becomes delta x of delta x log of P of x. This P of x is the same. We are taking the integral with respect to this thing. This is integral by parts. Oh, sorry. Yeah. Up.
Yeah. So the integral that you wrote, right?
Yeah.
So in the second integral of fx, integral of s, that is f prime x, that should be.
Yeah. Yeah, it's a
No.
Yeah. I
In
forgot.
integration, when you did the integration by parts.
Yeah. 1 second.
Yeah. This.
Yeah. F of x.
Here should be f prime x.
F dash.
Yeah, different, because dimensionality will not match. Differentiate that.
Yes. Yeah, because of this thing, yeah, it becomes another derivative will come over here.
F prime x.
Yes, f prime x. This is P theta. Okay. So now everything is in the neural network. We got rid of the P of x. Okay. So now we train the neural network for this minimizing this expression. Okay. And this expression. But again, here we have, if our neural network, for example, if our neural network is something like this, because this P of probability is a scalar value, right? The scalar value, we have given image, and here is the some scalar value. But here we have to compute with respect to x. It's the double derivative with respect to x. I mean, you have to, using the PyTorch things, we have to do it. Can we get rid of these things? So what authors propose is that our neural network itself predicts is nothing but entire this thing. I mean, what I mean to say, s theta of x is nothing but delta x log of P theta x. So even though P theta x is dimension 1, our delta x P theta x of dimension image size, right? Because we have to compute derivative with respect to every dimension. So our neural network itself computing the derivative.
But it computes the derivative with respect to theta, right?
X. There is no theta. No. That is to minimize.
Okay.
But we need to, this is a score function. It is called score function. For that, we need to compute with respect to x.
Yeah, we need to, but the neural network.
That is theta.
That is theta.
That is
right?
theta. Yeah.
Okay.
Yeah. So here, and how the architecture looks, they generally use some autoencoder unit kind of architecture. So that is something like this thing. You pass x and it computes the x dash. So in this way, it is enforced that the neural network learns the gradient. So now this expression replaced with s theta of x. But still here we have to compute with respect to x. So the final expression you understood, right? Sigma I equal to 1 to n s theta of x whole square minus 2 into delta x s theta of x. Yeah. So this is the score function. We minimize this thing, and after minimizing, we use the neural network. How we generate samples? Because what is this s theta? It gives the direction, right? And after how do you?
So score function, you are saying that s theta x. So is the score function learned from the neural network?
Yeah.
The score function we are learning from the neural network.
Yes.
Okay. And now the score function is guiding.
Yes.
Okay.
Yeah. So how we start? We sample x0 from a normal distribution generally. It's a noise version. And how we update xt equal to xt minus 1 plus our s theta x plus some noise, epsilon into noise. Why this noise? To diverse set of samples.
Yeah.
Okay, but okay, here it is clear. My writing is bad. It's
Oh, yeah, actually, I have.
yeah, sure.
Can you repeat how we get that second derivative term, the second, also showing,
Yeah. Last yesterday I did it. Very good. Today I messed up. Maybe I will discuss
Yeah, we
again.
will, yeah,
Yeah,
we will.
it's actually easy. Yesterday I did it. Now I messed up.
Okay.
Sorry. Yeah.
Perfect. Okay, and what's the meaning of this triangle? Is that
Okay. It's a neural network. Sorry.
Oh, yeah.
Neural network.
I thought that's the same class.
Yeah. Sorry. Okay, neural network. We are passing X. It is the general probability is nothing but a scalar value, right? So
Yeah.
it's a scalar value.
Okay, so output is
Scalar value.
Scalar
Yeah,
value.
level. But for to compute this thing, we have to compute derivative with respect to X, right? So we have to use the PyTorch backpropagation techniques to compute the derivative with respect to X, just like how you compute the adversarial attack noise.
With respect.
Yeah, with respect to X. So we have to compute the gradient with respect to X, and there we have to compute the double derivative.
Yeah. So I have
Yeah,
little confusion
sure.
with the score function. If a neural network is predicting the score function.
Yeah.
So, but the score function depends both on x and the theta.
Yes.
Right? The score function depends on, because it's a derivative with respect to x of the p theta.
Yes.
So, and score function, so the input to the neural network of the score function should be x and something to inform about theta. Right?
Yeah. Theta is a, like, at the moment is a theta. Yeah, theta is a current instant.
Okay.
Yeah. It is also parameterized by theta. Yes. But we are not learning a distribution over theta. We are learning the distribution over X.
Yeah, I get it.
Yeah.
But we are trying to learn the theta. I mean the
Yeah.
right.
Theta. Yes.
These
So-
are the weights of the neural
Weights
network.
of the neural
exactly.
network.
So we have to learn. But the score function, in order to calculate the score function, we need x and the theta.
Yes.
Right? But what you're passing to the neural network that predicts the score function.
I mean, like,
Right.
it's just like our any training neural network. We start from a random neural network, right? Random neural network. We compute this loss. At that particular theta. Okay. And what is the goal? To minimize this thing. Then you update theta such that this is minimized.
Yeah, something like the EM.
Okay,
Expectation.
So
First do
This is the
expected.
loss actually.
Okay, so I just
Yeah,
so
sure.
there is a s theta x, right, score function.
Yeah.
So what did the theta denote?
A neural network.
Yeah, exactly. So which neural network? The neural network that is used to calculate px, or the neural network that is used to calculate the score function?
P theta x, you mean?
Yeah.
Yeah, it's a P theta x. I mean, at a particular iteration, just like how we compute for a mini batch, we compute the class labels, right? And you want to minimize it. For a particular theta, you pass all the training samples, you make a prediction, and you compute a loss function.
Yeah.
And you will update theta such that minimizing the loss function.
Yeah.
Okay. Here, particular theta, you pass some X number of samples.
Yeah.
Okay. And for particular theta only, you also compute this score function.
Okay.
Delta X log of P theta X.
Okay.
Or delta X log of P theta X. And you get the loss function.
So yeah, so basically, so we have the two neural networks here, right?
One. It's the same theta.
We don't need to predict the PX here, right? We only need to predict the score.
Yes.
Okay.
So we don't need to predict that categorical distribution.
Yeah, it's not.
Okay.
This triangle makes things a little confusing.
I thought there is a neural network
Yeah.
that is using x to get p theta x.
No.
That's true, actually. That's true.
Oh, if that is true, then we have two neural networks.
No.
right?
Only one.
Revising it.
Huh?
We are changing it.
We are changing it to this thing. We are changing. Okay.
Yeah.
This is a change. This is the problem. Improvisation. That's not the part of it. It's improvisation.
Yeah. So this single triangle, that's just an example.
Yes.
True situation.
This is. Okay. Because here we have to compute gradient with respect to X twice. So to avoid that thing, the neural network itself compute the score function. So that is the improvisation.
Okay.
Okay. Okay. So this is the, you have time, right? Okay. Finish it. So this is a sampling thing. But what's the problems are? Problems are nothing. For example, our data distribution is somewhere here. Okay. And we generally, what is this X0? It's a normal distribution. And it has to start from somewhere here, right? Most probably, it doesn't have any information to move here or here because it's 0. So how to get rid of these things?
As noise makes the variance bigger, so that.
Yeah, that is the next step.
Oh.
Yeah. Here, this is part of sampling. This is inference. This is inference.
So the gradient here is 0, and you're seeing how to.
Yeah.
Laplace smoothing. Why like we just elevate the whole distribution.
Yeah, that's it. Yeah.
That too.
That's
What
it.
zero?
We add like we
Some
just
noise.
add 1 to all the classes. The whole
Here it's the
distribution.
continuous distribution.
Yeah.
Right. So similar thing,
Similar
actually.
thing.
Similar thing. So, okay, this is actually what, okay, even though you have learned this thing during generation process, even it might not help. Even it might not help because here the gradient is 0.
Yeah.
So it might help, but it might take more number of iterations. This normal distribution. So can we do something such that it also has some information? So what is the thing is that convolve with a continuous distribution. Okay, convolution in the sense like p of x integral of p of x some Gaussian p of x. So this is a Gaussian. Okay, this is actual distribution. So what this is doing is that this expression, it is uplifting a little bit. Same. So this is the actual distribution. When we add that Gaussian noise, what is happening is that it's uplifting. Okay. But the problem here is that if you add small amount of noise, it will only lift very little. If you add more amount of noise, the entire p of x information is lost. It becomes Gaussian. So what we do is that slowly add the noise. Okay. So what is the thing is that if this is p of x, okay, and we add gradually the noise. So the initial noise, when we add some, let's assume a multimodal. Okay. And when we add some noise, it lifts a little bit. Something like, and we gradually add noise, and every step we learn the score function. I mean, here we are only learning the score function at the true probability density, but you should learn probability at every noise level. So this is actual, okay, we learn the score function over here. We learn the score function over here. In this way, we learn the score function at multiple levels. Okay.
This is the denoising.
Denoising step. Here, this is the noising step. Yeah. That will help the denoising step.
The diffusion time step.
Yes. Yeah.
So the whole noising process is just to add support to the distribution.
Support to the distribution. So we are uplifting it. Okay, I'll directly go to the expression. Huh?
Squeeze the tutorial session two times.
Okay.
Yeah, because we don't want to hear more.
Yeah,
Maybe
sure.
we should do like probably stop here today.
Yeah. I mean, if you want, okay, fine.
Yeah, because I mean, because people may take a lot of brain power to understand concrete part.
Yeah, sure.
Yeah.
Okay.
It is very good. Actually, Srinivias become an expert in diffusion within past 2 months. So it's really well done.
Thank you.
Yeah. Once we publish our first few diffusion paper, we can potentially get in touch with Stanford or Emma and see his feedback.
Yeah, and one more thing I just want to highlight is that why I'm interested in diffusion thing. Okay, because if you look at the diffusion thing, whatever the underlying concepts they are using, they are built on existing things, whether it's Bayesian, or if you look at the continuous time, it's a queuing theory. Diffusion may last for maybe 3-4 years. After that, this whatever the knowledge I acquired for this sampling thing, it will be useful in the future too for different applications.
That's right.
So that is the reason I'm also interested in diffusion. Yeah.
But in new papers, they don't use normal distribution for adding noise, I guess, to improve the first section.
Yeah, this is true. I mean, this paper which I explained is the 2017 or 18 paper. 18 paper.
Yeah.
I mean, this you can look diffusion from different perspectives actually. Diffusion as a sampling thing, diffusion as a variational autoencoder of multiple levels, or diffusion as a solving stochastic differential equation. So you can look from a different perspective. They might have looked from a different perspective. They had a different kind of noise. It's always a improvement. So the reason for being explanation in this paper is that when I read this thing, I understood a lot actually why the noise is this thing. Earlier, I was not sure why they are doing. Okay, this uplifting thing, it's important.
Was this the first?
No, it's not the
perspective?
first.
No.
Okay.
Was this the first perspective?
First perspective, the paper which was proposed equilibrium, that is from the, it looks like variational autoencoder kind of thing. This is from the sampling perspective, Langevin dynamics.
Yang Song's paper.
Yes, Yang Song's paper.
That's all about.
I'll share the papers, all these things. Yeah. Even the page.
in Caltech now, right?
Yeah,
Okay,
actually, it's only it's
Open.
currently in OpenAI.
Yeah.
Oh,
Yeah.
everyone goes to
That's
the
interesting. Yeah, because
$1 million salary.
yeah, I guess got AP, but he didn't go just on you. So I didn't see the point of the.
And Elon too didn't give money.
Oh, okay.
Yeah, so everyone think.
I need feedback for my handwriting.
X and the theta.
Theta.
That's important, yeah.
That's it. So it's better to give the a clear formulation between
Yeah.
what is y, what is x.
Yes,
and,
yes.
Like the upper, what is time step, you
Uh-huh.
give the upper side or down side.
Yes, consistent. Okay,
Yeah,
nice.
yeah.
Thank you.
Yeah.
I tried yesterday X and theta on my notebook, like X as this thing, but today again I went like this.
Sometimes I can distinguish the difference between
X and
theta
theta. Yeah.
I think people prefer this kind of handwriting talks than the slide-based talks. It's this kind of project.
Yeah, could we
Yes,
use this whiteboard?
We
Yeah.
have our own whiteboard as well.
Yeah, because the whiteboard is small. Because for the marble you could see more equations.
Yeah.
Okay.
Our company is for people
Attending on.
Oh,
Do you want chalks?
yeah.
Some kind of blackboard.
yeah, I like chalks.
Yeah, I know that people prefer that. I think this is really good, and then we continue next week.
Yeah, and next week we have holiday, right?
Oh,
Friday.
okay, you are on holiday. Okay,
Oh.
we come back. Yeah,
Mm,
yeah.
I'm also not
it's
here.
a holiday, and you are on vacation.
Vacation, yeah.
It's Halloween and Diwali.
Yeah.
Somehow they are in the same day. I think.
Thursday and Friday. Thursday is also
Oh.
holiday, Friday is also holiday, right?
I think we'll have actually it's 3 days.
Oh,
So it's Halloween, Diwali, and Well-being Day of
Oh,
US.
that's really-
who said Friday is holiday? Ting, you?
Yeah, I think you're right. Probably
Yeah.
Thursday, Friday, and Monday. They are all holiday.
Monday is also holiday.
I just got a message from John Scarlett. He
Okay,
said that.
okay.
Yeah.
Check the temperature
It's a
calendar.
very long weekend then.
It's very long weekend.
We should have gone home.
Yeah, I'll go back in Taiwan when I will see. Good. So I think great. And if you have
Yeah.
and it's a very nice explanation of
Thank you.
from the fundamental innovation of diffusion models and I think I'm going to jump into the core of another research.